The Quiet Architect, Linus Torvalds and the Linux Revolution. Chapter 1, Helsinki's Humble Beginnings. Linus Benedict Torvalds entered the world on December 28, 1969, in Helsinki, the capital city of Finland. It was the tail end of a turbulent decade, but in the quiet, pragmatic Nordic nation, life flowed with a distinct, steady rhythm. He arrived into a family that, while not wealthy, was rich in intellectual curiosity and a passionate commitment to social ideals. His parents, Nils and Anna Torvalds, were both journalists, their lives deeply intertwined with the political and cultural currents of their time. Nils was a prominent figure within Finland's Communist Party, a world of earnest debate and staunch convictions. Anna, too, brought a sharp intellect and a commitment to her craft. The Torvalds family belonged to Finland's Swedish-speaking minority, a culturally distinct group within Finnish society. This heritage meant Linus grew up bilingual, navigating the nuances of two languages from an early age. While his parents engaged with the grand narratives of politics and public discourse, young Linus showed an early inclination towards a different kind of order, the logic of numbers and patterns. Perhaps the most formative influence in Linus's very early life came not from his parents, but from his maternal grandfather, Leo Turnqvist. Professor Turnqvist was a distinguished academic, a statistician at the University of Helsinki, and a man of quiet, methodical wisdom. Linus spent much of his childhood at his grandparents' home, a place that offered a peaceful counterpoint to the busy, politically charged atmosphere of his own home. It was here, amidst books and the calm pursuit of knowledge, that Linus found a haven for his nascent analytical mind. In 1981, when Linus was just 11 years old, Professor Turnqvist made a purchase that, unbeknownst to anyone, would set the course for his grandson's life, and eventually, a significant portion of the digital world. He acquired a Commodore VIC-20, one of the pioneering home computers that were just beginning to trickle into households. For many, it was a novelty, a game machine. But for young Linus, it was nothing short of a revelation. While other children his age might have been outside playing football or ice hockey sports that held little appeal for him, Linus found himself drawn to the monochrome glow of the computer screen. He wasn't a boisterous child. His personality gravitated towards introversion, a deep-seated desire to understand how things worked, and an unwavering focus on the task at hand. His grandfather, rather than simply letting him play, patiently guided him through the basic commands required to make the machine respond. This early, hands-on immersion in the nascent world of personal computing, in the quiet company of his grandfather, planted the very first seeds for the quiet architect of the digital age. It was a humble beginning in a peaceful Nordic city that would one day quietly underpin a global technological revolution. Chapter 2, The Commodore Days and Code Dreams. The Commodore VIC-20, with its modest 3.5 kilobytes of user memory and a rudimentary keyboard, was a rather unassuming machine. Yet, for 11-year-old Linus Torvalds, it became his first digital playground, a portal to a world of logic and creation. Unlike many of his peers, Linus wasn't merely interested in playing the pre-programmed games that came with the computer. His curiosity lay deeper, in understanding how the machine worked and, more importantly, how to make it do what he wanted. His initial foray into programming began with BASIC, a relatively high-level language designed for beginners. He typed in lines of code from magazines, watched the simple programs execute, and then, driven by an insatiable curiosity, began to modify them. But BASIC, for all its accessibility, felt limiting. It was like speaking generally to the computer. Linus yearned for a more direct, granular conversation. This yearning led him quickly to the more intricate world of machine code and assembly language. This was where the real magic, to Linus, resided. Instead of abstract commands, he was directly instructing the computer's central processing unit, line by painstaking line, in the machine's own language. He acquired a manual for the 6502 microprocessor, the chip at the heart of the VIC-20, and pored over its details. Understanding the instruction set, the registers, and the memory addresses became an obsession. He discovered the immense satisfaction of crafting efficient code, optimizing routines to make them run faster, and achieving complete, direct control over the hardware. The process was often arduous, filled with obscure error messages and countless hours of trial and error. Yet, the moments of triumph, when a complex subroutine finally executed perfectly, brought a profound sense of accomplishment. It wasn't about being productive or solving a real-world problem at this stage. It was about the pure joy of mastery. He was building miniature worlds from scratch, bringing them to life with his own logic, and commanding the machine to perform his will. He was, in essence, becoming a digital sculptor, shaping raw silicon with lines of text. In 1985, his grandfather, recognizing Linus's unwavering dedication, purchased a more advanced machine, the Sinclair QL Quantum Leap. The QL was a more sophisticated system, featuring a Motorola 68000 series processor and a more complex operating system than the VIC-20's simple basic interpreter. This offered Linus an even deeper dive into the architecture and nuances of computing. He wasn't just programming applications anymore, he was delving into the very heart of the system. He spent countless hours tweaking, modifying, and improving the QL's internal routines, often sharing his technical discoveries with user groups. This period cemented Linus's belief that the most satisfying and impactful aspect of programming was understanding and controlling the underlying system. The kernel, even if he didn't use that specific term yet. It was during these Commodore days that Linus developed his distinct approach to computing. A relentless focus on the low levels, a deep appreciation for efficiency, and a purely pragmatic pursuit of solutions driven by inner curiosity. He later described this motivation for what would become Linux as simply fun, a pure, unadulterated intellectual joy in the act of creation, problem-solving, and the quiet satisfaction of making a machine obey. Chapter 3. University Life and the Unix Aspiration. In 1988, Linus Torvalds embarked on a new chapter, beginning his studies at the University of Helsinki, majoring in computer science. This transition marked a crucial shift from the personal playground of home computers to the more formal, professional computing landscape. It was within the hallowed halls of academia that Linus encountered the operating system that would profoundly influence his future: Unix. At the university, powerful mainframe computers and Sun workstations hummed with the quiet efficiency of various flavors of Unix. This was a revelation. Unix was a sophisticated, multi-user, multitasking operating system, a stark contrast to the comparatively primitive environments he'd experienced on his Commodore and Sinclair machines. Linus was immediately captivated by its elegance, its command line interface, its hierarchical file system, and its robust set of utilities. Here was an operating system designed for serious work, for collaboration, for true computational power. It was efficient, stable, and widely respected in the professional computing world. It was everything he aspired to in an operating system. However, Unix came with a significant caveat: accessibility. Truly powerful Unix systems ran on specialized, expensive hardware, placing them far beyond the reach of a student's budget. Meanwhile, the affordable and increasingly popular IBM PC-compatible machines, though powerful in their own right, mostly ran MS-DOS, a single-user, single-tasking operating system that felt archaic compared to Unix. It was into this technological void that Andrew Tannenbaum, a professor at Vrije Universiteit in Amsterdam, had introduced Minix in 1987. Minix was an educational Unix clone, explicitly designed to be simple enough to be used as a teaching tool for operating system design courses. It ran on Intel 8086 processors and was freely available to academic institutions, making it a natural choice for curious students like Linus who wanted to understand operating systems from the inside. Initially, Linus was excited about Minix. It was Unix-like, it was free for his purposes, and it ran on the kind of hardware he could afford. He dove into its source code, hoping to find the freedom and power of a true Unix environment for his own 386 PC, which he would acquire a few years later. But as he explored, that initial enthusiasm began to curdle into frustration. Tannenbaum's design philosophy for Minix prioritized simplicity and pedagogical clarity above all else. It was a microkernel architecture, meaning that many core operating system services ran as separate, isolated processes, a design choice intended to make it easier to understand and teach. But for Linus, this design felt inefficient and overly rigid for a practical desktop system. It was slow and lacked essential features. He chafed against its limited support for common peripherals like hard drives and the absence of a truly robust terminal program. Minix felt, in his own words, like a toy. It fulfilled its academic purpose, but it didn't scratch Linus's itch for a powerful, flexible, and truly functional operating system for his personal computer. This growing dissatisfaction, a blend of admiration for Unix's power and frustration with Minix's limitations, began to brew within Linus. He saw the immense potential of what a Unix-like system could offer on affordable PC hardware, and he felt a growing desire to build something that could perfectly realize that potential. The seeds of a personal project, one that aimed not just for education but for true utility, were beginning to germinate. He wanted a Unix, not as a theoretical concept, but as a practical, everyday tool for his own 386 PC. This quiet aspiration, fueled by the gap between what was available and what he deeply desired, would soon set him on a solitary path that would, inadvertently, change the course of computing history. Chapter 4. A personal project, the birth of Linux. The year 1991 marked a pivotal moment for Linus Torvalds. He finally acquired his holy grail, an Intel 80386-based personal computer. This machine was a revelation. Unlike the older 16-bit processors, the 386 offered a full 32-bit architecture and, crucially, a protected mode that enabled robust multitasking and sophisticated memory management. These were the very features that made Unix-like systems so powerful, and the 386 put them within reach on an affordable, off-the-shelf PC. Minix, despite its educational value, felt increasingly restrictive on this powerful new hardware. It simply couldn't exploit the 386's full potential. Linus's ambition, at least initially, was deceptively modest. He wanted a better terminal emulator for his new 386. He needed a way to truly connect to the university's Unix systems from home, to transfer files, and to run programs remotely, without the sluggishness and limitations he had encountered with Minix. He started simple, writing code that allowed his PC to communicate with a serial port, the gateway to the university's network. But as he delved into the project, the scope rapidly expanded. To make a truly effective terminal emulator, he needed fine-grained control over the hardware. This led him to write routines for handling keyboard input, printing text to the screen, and managing disk interactions. He began crafting basic file system operations, allowing his programs to read and write data to the hard drive with efficiency. Then came the challenge of multitasking, allowing multiple programs to run seemingly simultaneously, a hallmark of sophisticated operating systems. He was coding mostly in assembly language for the critical, low-level routines and in C for the higher-level functions. The process was painstaking, meticulous, and deeply absorbing. Days flowed into nights as his personal project consumed him. He wasn't thinking about revolutionizing computing. He was focused on the elegant challenge of making the machine do exactly what he commanded, exploiting every bit of its power. There came a realization. He wasn't just building a terminal emulator or even just another Minix clone. He was building the fundamental core of an operating system, the kernel. He was constructing the very mechanism that manages the computer's resources, controls its hardware, and allows applications to run. This wasn't a clone. It was an original creation, leveraging his deep understanding of the 386 architecture. On August 25, 1991, at 23:23:8 EEST, Linus, then a 21-year-old student, composed a message that would become one of the most historically significant posts to an online forum. He sent it to the Compo-S Minix newsgroup on Usenet, a global network of bulletin boards. The subject line was unassuming. What would you like to see in Minix? The body of the message began. Hello everybody out there using Minix. I'm doing a free operating system, just a hobby, won't be big and professional like new, for 386, 486, AT clones. This has been brewing since April and is starting to get ready. I'd like any feedback on things people dislike in Minix, as my OS resembles its somewhat same physical layout of the file system, at least, among other things. He went on to describe its nascent features. Currently, I've ported Bash 1.08 and GCC 1.40, and things seem to work. This implies that I'll get something usable within a few months, and comments are welcome. Yes, it's free from any Minix code, and it has a multi-threaded multitasking FS file system and a shell. The port of GCC was the hardest part and still is. The compiler works, but libraries are still missing, so it isn't completely usable. He concluded with a modest plea for feedback. It is not portable, uses 386 task switching, etc., and it probably never will support anything other than at hard disks, as that's all I have. It was a quiet, almost apologetic announcement of a personal project, born out of curiosity and a stubborn desire for a better tool. Linus merely wanted to share his hobby work, to get some feedback from peers, and perhaps find a few like-minded individuals. He could not have known that this unassuming message, typed out in a small apartment in Helsinki, was the very first whisper of a technology that would fundamentally reshape the digital world. Chapter 5, Just for Fun, The Early Days of Collaboration. Linus Torvalds' unassuming Usenet post in August 1991, declaring his hobby operating system, quickly found its audience. While the wider world remained oblivious, a small but passionate group of computer science students, hobbyists, and early internet adopters, also frustrated by Minix's limitations, saw potential in his nascent project. For them, it represented the tantalizing promise of a free, powerful, Unix-like system for their affordable PC hardware, something they had long craved. The initial responses to Linus's post were a mix of curiosity, skepticism, and excitement. People wanted to see the code, to try it out for themselves. This immediate demand highlighted a crucial challenge: how to distribute the rapidly evolving project to a growing number of interested parties. To facilitate sharing, Linus's friend, Ari Lemke, a Finnish network administrator at the Helsinki University of Technology, offered a crucial service. He provided dedicated file transfer protocol, FTP space on the NICFunetFi server, allowing interested users to download the code directly. When Linus mentioned he was considering naming his project Freaks, a blend of free, freak, and the X from Unix, Lemke, with his own practical directness, simply created a directory on the server called Linux. The name was a portmanteau of Linus's first name and Unix. Linus, ever pragmatic, wasn't overly fond of the self-referential name, but ultimately conceded, and Linux it became. This seemingly small decision would prove to be one of the most fortuitous accidents in computing history. With the distribution mechanism in place, the project truly began to breathe. Linus would periodically upload new versions of his kernel, and a community of early adopters would eagerly download them, compile them, and put them through their paces. This wasn't merely about using the software, it was about actively participating in its creation. Users would report bugs, offer creative solutions, and, most importantly, send patches, small pieces of code that could modify or add functionality to the kernel. This rapid, iterative development model was unlike anything seen in the proprietary software world. It was a testament to the burgeoning power of the internet, then in its relatively early stages. Newsgroup discussions, email lists, and FTP servers formed the nervous system of this distributed collaboration. Linus, often working late into the night, would meticulously review these stream of contributions. He would integrate the best patches, refine existing code, and push out new versions of the kernel with astonishing speed. The first official public release, version 0.01, hit the FTP server in September 1991. It was bare bones, essentially a basic terminal program. But within a few months, rapid iteration led to version 0.02, then 0.11 by December 1991. Version 0.11 marked a significant milestone. It was self-hosting, meaning it could compile itself. This was proof of its increasing stability and functionality. What began as a single individual's, just for fun hobby project, driven by a personal need and curiosity, had, in a shockingly short period, blossomed into a burgeoning collaborative effort. The rapid growth of Linux, fueled by collective enthusiasm, shared skills, and an open exchange of ideas, laid the foundational blueprint for the open-source movement. It proved that quality software could indeed be built not by a corporate behemoth, but by a global community of passionate individuals working together, one line of code at a time. The world was just beginning to realize a new paradigm of software development had been quietly born. Chapter 6: Licensing Battles and the GPL Embrace. As Linux rapidly grew from a personal hobby to a collaborative project with a burgeoning user base, the question of its licensing became increasingly critical. In its very earliest iterations, Linus Torvalds had devised a custom license. It was quite permissive in allowing free modification and distribution for non-commercial use, which suited his initial, just for fun, ethos. However, it explicitly prohibited any commercial exploitation of the software. This stance was initially understandable, but as more developers contributed, and as the project gained traction, it raised questions about consistency, protection, and philosophy. This custom license stood in stark contrast to the burgeoning ideals championed by the Free Software Foundation, FSF, and its outspoken founder, Richard Stallman. Stallman was a passionate advocate for what he termed free software, defined not by cost, but by freedom. His vision guaranteed users 4 essential freedoms: the freedom to run the program for any purpose, the freedom to study how the program works and adapt it to your needs, the freedom to redistribute copies, and the freedom to improve the program and release your improvements to the public. To ensure these freedoms were propagated, Stallman had devised the GNU General Public License, GPL, a powerful legal instrument designed to be a copyleft license, meaning that any derivative work must also be distributed under the same terms, fiercely protecting the freeness of the software. The licensing discussion gained public prominence, in part due to the now famous Tannenbaum-Torvalds debate that unfolded in early 1992. Andrew Tannenbaum, the creator of Minix, posted a public critique of Linux's design, specifically arguing against its monolithic kernel architecture, where the entire operating system runs as a single large program in one address space, in favor of his own microkernel design. The debate, which played out publicly on Usenet, was spirited and often technical, but it also touched upon Linux's initial, unfree, aspects compared to FSF's GNU tools, which were needed to make Linux a truly functional operating system. Linus, ever the pragmatist over the ideologue, quickly recognized the strategic wisdom of adopting the GPL. His custom license, while well-intentioned, could ultimately hinder Linux's growth by creating legal ambiguities or disincentivizing contributions from larger entities. The GPL, by contrast, offered robust legal protection for the project's open nature. It ensured that companies or individuals could build products on Linux, integrate Linux into their own systems, or even sell distributions of Linux. But they could not take the code, make improvements, and then close off those improvements into a proprietary, and thus less free, product. This crucial principle, often summarized as what goes in free, stays free, fostered an environment of shared innovation and transparency. Thus, in early 1992, with version 0.12 or 0.99, the exact early transition point varies depending on source, Linus made the pivotal decision to relicense the Linux kernel under the GNU General Public License, specifically GPLv2. This was a transformative moment. It formally aligned Linux with the broader philosophical tenets of the free software movement, removed a major legal barrier to its proliferation, and crucially, guaranteed that every contribution to the kernel from every developer would remain open and accessible to all. The adoption of the GPL was a cornerstone of Linux's eventual success, fostering a culture of true collaboration and setting the stage for its dramatic expansion beyond a hobbyist's project into a global phenomenon. Chapter 7: The Benevolent Dictator and the Inner Circle. As Linux grew, evolving from a solitary hobby project to a global collaborative effort, managing the influx of code and contributions became a monumental task. Thousands of developers, scattered across continents, began sending in patches, bug reports, and new features. To maintain code quality, consistency, and a coherent vision, a central authority was, and still is, necessary. Linus Torvalds, by virtue of having conceived the project and continuing to review code, naturally assumed this role, becoming the ultimate arbiter of what code enters the Linux kernel. This unique leadership position earned him the informal, yet widely recognized, title of Benevolent Dictator for Life, BDFL. The term dictator might sound harsh, but in the context of Linux, benevolent is key. Linus doesn't dictate architecture from a boardroom. Rather, he presides over a highly decentralized, meritocratic development model. His authority stems from his technical expertise, his long-standing commitment to the project, and the community's trust in his judgment. He rarely writes code himself anymore, preferring to review and integrate. The core of Linus's management style is the maintainer model. Below Linus, whose purview is the absolute core, often referred to as the Linus tree, are a few dozen highly trusted and technically adept individuals known as subsystem maintainers. These maintainers are responsible for vast sections of the kernel, from specific hardware architectures and device drivers to networking stacks and file systems. They are chosen for their deep technical knowledge, their ability to lead, and their consistent, high-quality contributions. The development workflow is meticulously structured. Developers, regardless of their company affiliation or experience level, submit patches, small, atomic code changes, to the relevant subsystem maintainer. These patches contain proposed additions, bug fixes, or improvements. The maintainers review these submissions, provide feedback, and sometimes request revisions. Once accepted, the maintainer integrates the patch into their specific subsystem's development tree. Periodically, maintainers send their accumulated changes back up the chain to Linus for his final review and inclusion in the official kernel. This layered approach allows for a massive project to be managed efficiently. Linus trusts his maintainers to vet code within their domains, and he then provides the final, overarching sanity check. His review process is legendary. He can process thousands of lines of code, spot subtle bugs or architectural flaws, and reject contributions with devastating clarity. Linus's communication style is notoriously direct, unfiltered, and often punctuated with blunt language and even profanity. He has no patience for sloppy code, ill-conceived ideas, or abstract discussions that lack practical grounding. This bluntness, while shocking to outsiders, is largely accepted and even respected within the kernel community. It's understood that his critiques are rooted in technical merit and a relentless pursuit of quality, not personal animosity. He demands technical excellence, and he speaks plainly to achieve it. Key figures like Alan Cox, Dave Miller, Andrew Morton, and Greg Crow-Hartman emerged as integral members of this inner circle, each contributing immensely to the stability, development, and future of the kernel under Linus's ultimate guidance. This unique blend of distributed contribution, hierarchical review, and a single, benevolent dictator at the apex is a testament to Linus's pragmatic leadership. It is a system where code, not personality or corporate hierarchy, ultimately dictates what makes it into the heart of the world's most pervasive operating system. Chapter 8: Linux Ascendant. Servers, desktops, and the dot-com boom. By the mid-1990s, Linux was no longer just a hobbyist's curiosity. It was rapidly maturing into a robust and reliable operating system. Its inherent stability, security, cost-effectiveness, and, critically, its open-source nature made it an increasingly attractive alternative to proprietary Unix systems and Microsoft's Windows NT in the burgeoning server market. One of the most significant accelerants for Linux's adoption was the explosion of the World Wide Web. The Apache HTTP server, an open-source web server, became the dominant force on the Internet, and it ran exceptionally well on Linux. The combination Linux for the operating system, Apache for the web server, MySQL for the database, and scripting languages like PHP, Perl, or Python became known as the LAMP stack. This powerful, free, and incredibly flexible combination became the de facto standard for building web applications, powering much of the early Internet's infrastructure. Startups and established companies alike flocked to Linux, recognizing its ability to provide a scalable, secure, and affordable foundation for their online presence. This growing enterprise adoption led to the emergence of commercial Linux distributions. Companies like Red Hat, Debian, SUSE, and Caldera sprang up, realizing that while the Linux kernel itself was free under the GPL, There was immense business value in packaging the kernel with a complete suite of user applications, system tools, and installation utilities. These distributions offered technical support, training, and professional services, allowing businesses to confidently deploy Linux in mission-critical environments. This model proved that a thriving economy could indeed exist and flourish around free software, challenging the traditional proprietary software giants. Simultaneously, a persistent dream of desktop Linux began to take shape. The idea was to create an operating system that could directly compete with Windows on personal computers, offering a free and open alternative for everyday users. Efforts like the GNOME and KDE desktop environments emerged, providing graphical user interfaces that made Linux more approachable. However, the path to desktop dominance proved to be far more challenging than server adoption. Fragmentation across distributions, inconsistencies in hardware compatibility, especially for peripherals like printers and scanners, and a paucity of widely used proprietary applications, like Microsoft Office, compared to Windows, acted as significant barriers. While desktop Linux gained a loyal following, it never achieved the mass market penetration of its server counterpart. Nevertheless, the late 1990s and early 2000s, known as the dot-com boom, provided an unprecedented boost for Linux. Amidst the frenzy of new internet companies and rapid expansion, time to market and cost efficiency were paramount. Linux, with its agility, robustness, and zero licensing fees, was the perfect fit. Startups could spin up new servers quickly, scale their infrastructure on demand, and customize their environments without incurring prohibitive software costs. Major internet players began building their entire operational infrastructure around Linux, solidifying its position as the workhorse of the digital revolution. During this period, Microsoft, the undisputed king of the software world, initially dismissed Linux and the open-source movement with disdain, often referring to it as a cancer or un-American. Yet, as Linux's presence grew from a niche curiosity to a serious competitor in the server and enterprise markets, this dismissive attitude slowly began to shift. The sheer scale and reliability of Linux deployments compelled a grudging respect, foreshadowing a future where even Microsoft would have to contend with, and eventually embrace, the open-source paradigm that Linux had so powerfully established. Linux was no longer an academic exercise, it was a fundamental component of the emerging internet economy. Chapter 9: The Git Revelation, Fixing the Kernel's Own Problem. By the early 2000s, the Linux kernel project had grown into a colossus. Thousands of developers worldwide were contributing code, fixes, and features, generating a torrent of patches and changes. Managing this massive, distributed development effort required a sophisticated version control system, a tool that could track every change, allow multiple developers to work on the same files simultaneously without chaos, and facilitate the complex process of merging disparate code branches into a single, coherent product. For a time, starting in 2002, the kernel development community relied on a proprietary distributed version control system called BitKeeper. Developed by Bitmover Inc., BitKeeper was powerful, efficient, and well-suited to the demands of a project as vast and distributed as the Linux kernel. Bitmover even offered a free-of-charge license for non-commercial open-source projects, making it a viable solution for the kernel team. While some in the open-source community harbored philosophical objections to using proprietary software, the sheer pragmatic utility of BitKeeper won out, allowing the intense pace of kernel development to continue. However, in 2005, this pragmatic arrangement disintegrated. A prominent Linux kernel developer, Andrew Tridgell, known for his work on Samba, a free software reimplementation of Microsoft file-sharing protocols, began working on an open-source alternative to BitKeeper, attempting to reverse-engineer its protocol. Bitmover viewed this as a direct violation of their terms of service, perceiving it as an attempt to undermine their commercial product. As a result, Bitmover rescinded the free-of-charge license for the Linux kernel development community. The decision plunged the kernel project into crisis. Suddenly, the engine that powered their distributed development was gone. The alternatives were bleak: either revert to an unwieldy system of emailing patches around, or adopt an inferior open-source solution that couldn't handle the project's scale. Linus Torvalds, known for his ability to think out of the box and solve fundamental problems with elegant, often audacious, technical solutions, refused to accept either. Instead of searching for an existing tool, Linus decided to build one himself. He wanted a version control system that was distributed, meaning every developer would have a full copy of the entire project history, making collaboration robust and resistant to single points of failure. He also prioritized speed, data integrity, ensuring no changes were lost or corrupted, and strong support for nonlinear development, such as branching and merging multiple lines of work seamlessly. In an incredible burst of focused energy, Linus spent approximately 2 weeks in April 2005, working almost non-stop to lay the foundational code for this new system. He famously named it Git, British slang for an unpleasant person, a typically self-deprecating joke on his part. The initial version was rough but immensely powerful, a testament to his deep understanding of how version control should work for a project like the kernel. Within months, it was robust enough to manage the entire Linux kernel codebase. What began as an emergency solution to an internal crisis within the Linux kernel project quickly proved to be a revolutionary tool for the entire software development industry. Git's speed, flexibility, and robust design became the standard for distributed version control. Platforms like GitHub, GitLab, and Bitbucket emerged, built entirely around Git, transforming how software is versioned, collaborated on, and shipped globally. The creation of Git stands as a towering auxiliary achievement for Linus Torvalds, a profound example of his capacity not just to create a world-changing operating system, but to identify and solve fundamental infrastructure problems for the entire developer community, simply because a better way was desperately needed. Chapter 10, Android, Clouds, and Ubiquity, Linux takes over the world. While the ambition of desktop Linux as a direct competitor to Windows in every home never fully materialized, the Linux kernel quietly, relentlessly, and almost entirely out of public view, became the undisputed operating system of the digital age. Its omnipresence today is staggering, powering the very infrastructure upon which much of modern life depends. Perhaps the most visible manifestation of Linux's triumph came with the advent of the smartphone. In 2005, Google acquired Android Inc., a small startup with grand plans for a mobile operating system. Recognizing the need for a robust, flexible, and open platform to compete with Apple's iOS and other proprietary mobile systems, Google's engineers made a pivotal decision. They chose the Linux kernel as the foundation for Android. This strategic choice leveraged Linux's stability, power management capabilities, and open-source licensing. Today, Android powers billions of smartphones and tablets worldwide, making Linux, by sheer device count, the most widely used operating system on the planet. Every tap, swipe, and voice command on an Android device is ultimately managed by the Linux kernel working quietly beneath the surface. Beyond our pockets, Linux achieved an even more fundamental dominance in the realm of cloud computing. When companies like Amazon with Oz, Microsoft with Azure, and Google with Google Cloud Platform began building the massive data centers that would become the backbone of modern enterprise and internet services, they overwhelmingly chose Linux. Its efficiency, scalability, and ability to handle immense workloads made it the ideal operating system for virtualized environments. Today, the vast majority of virtual servers running in the cloud, supporting everything from social media networks and streaming services to enterprise software and scientific research, run on Linux. The cloud is, in essence, a giant Linux farm. Furthermore, Linux's flexibility and open-source nature made it the perfect brain for an astonishingly diverse array of embedded systems and Internet of Things, IoT, devices. From smart refrigerators and security cameras to industrial control systems, automotive infotainment units, and digital signage, Linux is the hidden engine. Its modular design allows manufacturers to strip it down to only the essential components required for a specific device, making it lightweight and efficient. And at the very cutting edge of computation, in the world of supercomputing, Linux reigns supreme. For years now, virtually every supercomputer on the planet, including the fastest machines dedicated to scientific research, climate modeling, and national security, runs on Linux. Its ability to scale to astronomical numbers of processor cores and manage petabytes of data underscores its unparalleled performance and reliability. This pervasive presence means Linux isn't just a part of the technology landscape. It is the landscape for much of the digital world. It powers everything from the traffic lights in our cities and the in-flight entertainment systems on airplanes to the Mars rovers exploring distant planets and the International Space Station orbiting Earth. The irony is that for most people, Linux remains invisible. Users interact with the applications built on Linux, Google, Facebook, Netflix, their Android phones, without ever realizing the silent, powerful foundation provided by Linus Torvalds' creation. What started as a personal project from a Finnish student would, against all odds, become the silent, ubiquitous force that powers the very fabric of our interconnected world. Chapter 11. The Philosopher of Pragmatism. Linus Torvalds is not a philosopher in the traditional, academic sense. He hasn't written treatises on ethics or epistemology. Yet, he embodies a powerful and distinct philosophy that has profoundly shaped the Linux kernel and, by extension, the broader open-source movement. His approach is driven by an unwavering pragmatism, a relentless focus on technical excellence, and a deep, instinctual aversion to anything he perceives as fuzziness. His most famous and oft-quoted mantra encapsulates this philosophy: "Talk is cheap, show me the code." This isn't just a witty retort, it's a core belief. For Linus, the only true measure of an idea or a contribution in software development is its concrete implementation, its ability to translate into working, efficient, stable code. Abstract discussions, theoretical debates, or grand ideological statements hold little weight if they cannot be demonstrated or proven through functional execution. This code-first mentality defines the meritocracy of the Linux kernel development community. Contributions are judged purely on their technical merit and their positive impact on the project, not on the seniority or eloquence of the person proposing them. Linus consistently prioritizes getting things done over ideological purity. While he embraced the GNU General Public License, GPL, for pragmatic reasons, its legal protections, and its ability to foster collaboration, he has often distanced himself from the more dogmatic aspects of the free software movement. His focus is on building the best possible kernel, even if it means incorporating non-free binary blobs for hardware support when no open alternative exists. This pragmatic orientation is encapsulated by his approach to problem solving. Find the most effective technical solution, implement it well, and iterate. He expresses a profound skepticism for anything that lacks empirical evidence or practical application. This extends from software design patterns to abstract theoretical concepts. Linus values clear, concise communication and robust engineering. His notorious directness, expressed through blunt language and occasional profanity in mailing list discussions, stems from this core belief. For Linus, clarity and precision are paramount in a technical context. A poorly written patch, an ill-conceived design, or an abstract argument, when presented to Linus, will be met with unvarnished honesty. This communication style, while sometimes controversial to outsiders, is seen by many in the kernel community as a necessary mechanism for maintaining high standards and preventing technical debt. It's a method of stripping away pretense and focusing solely on the technical truth. While the phrase Linus's law or Linus's doctrine, given enough eyeballs, all bugs are shallow, was coined by open-source theorist Eric S. Raymond, it perfectly captures Linus's inherent trust in the power of distributed collaboration and peer review. He instinctively understood that by allowing a vast, intelligent community to examine and contribute to the code, flaws are discovered more quickly, solutions are found more efficiently, and the overall quality of the software improves dramatically. In essence, Linus Torvalds' philosophy is one of uncompromising technical pragmatism. He is a builder, a system architect in the truest sense, whose values of efficiency, stability, and directness have shaped not just a piece of software, but a unique culture of development. It's a philosophy that champions effective execution over grand pronouncements, and where the code itself stands as the ultimate, undeniable truth. Chapter 12. Public Persona, Private Man. Navigating Fame. Despite being the quiet architect of one of the most influential technologies of our time, Linus Torvalds remains, remarkably, a private and largely introverted individual. His journey to the forefront of the tech world never seemed to involve a desire for fame or public adulation. In 1997, he made a significant move, relocating from his native Finland to Santa Clara, California, to work for Transmeta Corporation, a chip design company. This move placed him at the heart of Silicon Valley, the epicenter of the computing world, where he could more easily collaborate and influence the technological landscape. It was also in the United States that he continued to build his family life with his wife, Tove Mani, whom he met at the University of Helsinki. Tove, a six-time Finnish national karate champion, found her own unique path, later becoming a long-time manager of high-end events at the Linux Foundation. Together, they raised 3 daughters. Linus has consistently conveyed a profound disinterest in the trappings of celebrity. He rarely seeks public speaking engagements, preferring to communicate through text, email, mailing list discussions, and code. He's often described as a builder, far more comfortable wrestling with intricate technical challenges of the kernel than navigating the social complexities of public relations or corporate politics. He maintains a casual, unpretentious demeanor, often seen in simple t-shirts and jeans, a reflection of his focus on substance over superficiality. However, the sheer scale of his work and the occasional need for him to engage publicly has inevitably thrust him into the spotlight. His characteristic candidness, a trait deeply valued within the kernel community for its directness and technical honesty, has at times caused public stir. Perhaps the most infamous instance occurred during a 2012 Q&A session, when, frustrated by NVIDIA's perceived lack of support for Linux, Linus famously gave the company the middle finger. The image and video clip went viral, epitomizing his no-nonsense, technically driven approach and his low tolerance for what he perceives as incompetence or indifference. More significantly, in 2018, Linus's blunt communication style, which sometimes veered into personal attacks and profanity, became a focal point of criticism within the broader open-source community. Faced with a growing chorus of concerns about the tone of his interactions, Linus, in a rare public display of vulnerability, acknowledged the issue. He announced he would take a temporary break from kernel development to reflect on his behavior and seek help in understanding people's emotions and how to communicate more effectively. He admitted that his flippant attacks in emails have been unprofessional and uncalled for, and that he needed to understand people better and to actually respond to their emotions. This period of self-reflection, and his subsequent return with a commitment to a more empathetic approach, underscored his deep dedication to the community he had built, even as it highlighted the evolving social dynamics of a global, diverse open-source movement. Despite the immense public impact of his work and his occasional forays into public controversy, Linus Torvalds steadfastly remains a private man. His primary focus has always been the code, the technical challenges, and the continuous improvement of the Linux kernel. For him, the ultimate satisfaction lies not in recognition or fame, but in the quiet, profound act of building the very foundation of the digital world. Chapter 13. Looking Forward. The kernel's enduring legacy. Today, the Linux kernel is not merely a successful software project. It is a continuously evolving, highly dynamic organism. Far from being a static artifact completed by its creator, it is a living entity, adapting to a constantly shifting technological landscape. Thousands of developers, ranging from independent contributors to full-time engineers employed by tech giants like Google, Intel, IBM, and Red Hat, contribute to its ongoing development annually. The pace is relentless. Each new stable kernel release, typically every few months, incorporates hundreds of thousands of lines of new code, making it one of the largest and most actively developed software projects in human history. This sheer scale of development allows Linux to remain at the forefront of technological innovation. It has demonstrated an unparalleled ability to adapt to new hardware architectures, including the energy-efficient ARM processors that dominate mobile devices and the increasingly popular open-source RISC-V architecture. It seamlessly integrates support for cutting-edge technologies like artificial intelligence, AI, workloads, advanced networking protocols, and new security paradigms. Whether it's powering complex quantum computing simulations or running the latest cloud-native applications, Linux proves its versatility and resilience time and again. However, the continued growth of the kernel also presents perennial challenges. Maintaining a codebase now estimated to be well over 30 million lines of code is a monumental undertaking. Ensuring compatibility across an ever-expanding multitude of hardware configurations, from tiny embedded systems to colossal supercomputers, demands constant vigilance. Security remains a paramount concern, especially given Linux's critical role in global infrastructure. The development community continually battles against new vulnerabilities, ensuring the kernel remains robust and secure against malicious attacks. Linus Torvalds, now in his early 50s, continues to preside over this colossal project. While his direct coding contributions have diminished, his role as the benevolent dictator for life, BDFL, remains crucial. He oversees the final integration of changes from his subsystem maintainers, making the ultimate decisions on what code makes it into the official kernel. His highly refined technical judgment and decades of experience continue to be the project's guiding compass. The question of succession for a project, so intrinsically linked to its visionary leader, often arises. While no formal succession plan exists in the traditional corporate sense, the decentralized, meritocratic nature of the Linux kernel development implies a natural evolution. The core group of seasoned maintainers, who have earned Linus's trust and respect over decades, would likely transition into a distributed leadership model, continuing the project's trajectory. The robustness of the process, based on technical merit, peer review, and transparent communication, is designed to transcend any single individual, even its founder. The long-term health and growth of the Linux ecosystem appear secure. Its foundational role in cloud computing, mobile technology, embedded systems, and supercomputing ensures its continued relevance. As humanity pushes into new technological frontiers, be it widespread AI deployment, advanced robotics, or novel computing paradigms, it will almost certainly be building on the stable, open, and endlessly adaptable foundation that Linus Torvalds created. The Linux kernel's enduring legacy is thus not just what it has already accomplished, but its unwavering capacity to underpin the future. Chapter 14, Beyond the Code. A Life of Impact. Linus Torvalds, the unassuming Finnish software engineer, rarely seeks the spotlight, yet his work has placed him firmly in the pantheon of figures who shaped the modern world. He has received numerous accolades for his work, including the prestigious Millennium Technology Prize in 2012, often referred to as Finland's equivalent of the Nobel Prize, and induction into the Internet Hall of Fame. These recognitions, while significant, only scratch the surface of his profound legacy. His most remarkable contribution lies not merely in the lines of code he wrote, but in fundamentally reshaping how software is conceived, developed, and distributed. Linux, operating under the principles of the GNU General Public License, GPL, popularized and legitimized the open-source development model. This collaborative, peer-produced approach, where code is openly shared, freely modifiable, and iteratively improved by a global community, was a radical departure from the proprietary, closed-source paradigm that dominated the computing industry. Linus demonstrated, through the indisputable success of the Linux kernel, that a decentralized, non-commercial approach could produce software of unparalleled quality, reliability, and security. His work directly challenged the giants of the proprietary software world, proving that a transparent and community-driven process could not only compete, but often surpass products developed behind closed doors. This model, which emphasizes shared ownership, transparency, and collective problem-solving, has since been adopted and replicated across countless other software projects and industries. From web browsers like Firefox to massive artificial intelligence frameworks and blockchain technologies, the spirit of open collaboration, pioneered and proven by Linux, now permeates almost every corner of the digital landscape. The economic impact of Linux is staggering. It has fueled the growth of countless startups, served as the bedrock for enterprise IT infrastructure, and provided an affordable, robust alternative to expensive proprietary systems, saving businesses untold billions in licensing fees. By making powerful, cutting-edge software freely available, Linux has democratized access to technology, fostering innovation and reducing barriers to entry for developers and entrepreneurs worldwide. When Linus famously declared in his autobiography, "Just for fun, the story of an accidental revolutionary," that he was not a visionary and didn't have a plan, he genuinely meant it. His motivation was personal, a desire for a better operating system for his own PC, driven by intellectual curiosity and the sheer enjoyment of building. He never set out to launch a revolution or topple industry titans. Yet, through his exceptional technical prowess, his innate understanding of collaborative dynamics, and his stubborn insistence on getting things done with clarity and precision, he inadvertently triggered a profound shift. His life story is a compelling testament to the power of individual curiosity, pragmatic problem-solving, and the transformative potential of sharing knowledge and building in the open. Linus Torvalds didn't orchestrate a global change through grand manifestos or charismatic leadership. Instead, he simply wrote the code that allowed the world to change itself, proving beyond doubt that sometimes, the most profound revolutions begin not with a bang, but with a quiet, persistent hum of a computer, creating something just for fun.